you know. Okay, so it looks like we're live. Let me get me on the speaker view. Whoops. Speaker view. Get me up there. Hit pause on the live over here. Okay, so our goals today, we want to finish that little bit of chapter 9. I mentioned something about a zombie in a canoe type problem. So we're going to finish chapter 9, and then we're going to move on to chapter 10. And yeah, we're just going to keep plowing ahead as much as we can. So I think that'll be a good thing to have extra time at the end of the semester rather than, yeah, because things just tend to get busy. So I'm going to keep plowing ahead. Let's just do it. Let's start with a screen share. Let me get the workbook up here. Whoops, wrong. Let me get back to the Zoom meeting, share screen. Okay. Whoops, wrong one. There we go. So let's see. I think we're somewhere around page 51. Is that right? Okay, close to that. I think we're right here, zombie in the canoe. There we go. And so this is page 50. Apologies for that. Okay, so we haven't done much of this yet, but I want to point out something that is different about this problem than every problem we've done so far by looking at these pictures. For most of the problems that we have done so far, we've been talking about a block that moves around, or maybe a block that splits in half and flies into two pieces or something like that, or two blocks that collide and form a single mega block. This is a little bit different. This is an object that changes shape. It deforms. So it's a sync, right? Do you see that this is a little bit different than any of these other things? And so there's a couple of tricks we can do to analyze what, I guess you could call this a deformable system. It's a system, meaning it's got two objects or more in there. So there's a zombie and a canoe, mass 1 and mass 2, if you want to just say it that way. And we see that the locations of mass 1 and mass 2 relative to each other have moved around. Now, in this case, I want to emphasize something, why we're doing this weird contrived problem of a zombie in a canoe. The idea here is think about the forces on this problem. There's a normal force up, or you could call it a buoyant force, which we'll learn about in chapter 14. But it's effectively, in this problem, acting very similar to a normal force. So the water buoys up this canoe. There's mg down, and we'll just call that m total g. Now, obviously, I'm not drawing this very well. That should actually act at the center of mass. The center of mass is probably somewhere right here between the zombies and the canoe's center. All right. But in general, that's showing us we have no net external force. So force external net is equal to 0. And I'm going to put a vector on that. So if you have no net external force, well, we could actually use our relationship that says that tells us that the acceleration should equal 0, right? Now, in this case, that acceleration is the acceleration of the center of mass. Now, to get to this, to relate this to these pictures, let me put it this way. We're going to assume that the acceleration of the center of mass is 0. In this particular problem, the velocity of the center of mass is 0. So what will happen here, or at least initially it is, so if the velocity of this object is initially 0 and its acceleration is 0, that means this. The center of mass position should stay put. If it's not accelerating and not moving, the initial position equals the final position. So this is a very weird kind of buildup, but the idea is we can actually say, look, I know the center of mass of this thing initially is located right here. If the zombie walks to the other end, I know that the center of mass cannot move. I'm ignoring any drag between the canoe and the water. Drag between the canoe and the water is negligible. And this is pretty much true. So if you ever do this, if you ever put a boat right up at one edge of a dock and you try to walk from one end to the other and manage to not fall in, by the time you get to the other end of the boat, you won't be at the dock. Why? As the zombie walks this way, let's say this is the zombie walking this way, the zombie has to exert a force on the canoe backwards. So the canoe, we'll just draw this as a block, the canoe is going to move that way. And again, this is conservation of momentum, conservation of momentum, and Newton's third law are essentially the same thing. If the zombie has momentum to the left, the canoe has momentum to the right. And so as a result, you get this weird scenario where the zombie walks to the end of the boat, but the end of the boat is no longer at the dock. Oh my gosh, that was a long buildup. I'm going to pause and see if anybody has questions about this before we try and do some math. Does that make any sense at all? I hope so, but I don't know.
So if the canoe has moved, shouldn't the center of mass have moved as well?
No. And so let's see if we could actually figure this out. Let's look at the solution just to save some time. And I hope I drew the pictures in there. What problem was that? I'm sorry.
9.43.
What's that? Oh, whoops. 9.43?
Yep.
Thank you. Please tell me I drew pictures. Ah, okay. So, well, here's one. All right. So, okay. So I'm going to have to work this one out. All right. I got to do real work today. Oh, man. All right. Let's start out and just do the problem from scratch. So I think I worked out the problem for you in the problem statement, but just in case it's not obvious, let's do this. Oh, and somebody's trying to get in here. Sorry, Eduardo. Let's get him in here. Oh, somebody else is trying to get in too. Sorry, it took me a minute to add you guys. Sorry, it took a second. I just didn't see it. Okay, so let's start out here. Oh, markers. Let's try another one. All right. So let's start here. Like this. And so we've got this purple object. This is mass 1, I think. Did I call mass 1 the canoe in the problem? Where's my problem? Where'd my book go? Here it is.
The zombie is mass 1.
Okay. Oh, zombie's mass 1. Okay. So the canoe is mass 2. Thank you. And then we've got a zombie up here. Let's simplify it. Just call it object 1. Okay. So we got mass 1 here. So the idea is, where is the center of mass? Well, we need a coordinate system when we're doing a center of mass. So what do you guys want to call the origin in this problem? I see 3 logical choices, or 4.
Maybe make the zombie the origin?
You can make the zombie the origin. That's a good job because that takes one of the positions and sets it to 0 and makes it easier to do the math. That's one good spot. What's another good spot for the coordinate system? Somebody else.
The middle of M2.
The middle of M2. That's nice for the same reason. And what's another one?
Can we do it at M2?
We could do it right here. This is nice because then all the positions are positive, so we don't have any minus signs. Those are all, so putting it here is a good reason because something is equal to 0. Putting it here is a good reason because something's equal to 0. Putting it here is a good thing because there's no negative signs. What's the last good spot to choose?
Maybe the opposite side of M2.
That would well, we said here, here, here.
Oh, okay.
What about the center of mass being the
You
origin?
could call the center of mass 0. Now check this out. You might not know why to do that, but let me just say we have x center mass initial equals x center mass final, right? Now, in this case, we'd say x1 initial times mass 1 plus x2 initial times mass 2 all over m1 plus m2 has to equal x1 final m1 plus x2 final m2 all over m1 plus m2. If we set the center of mass equal to 0, that means both of these equations are equal to 0, and that means the denominators don't matter. So there's why you might do that. Does that make sense? That's sneaky. So again, we see 4 good spots here, 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 and somewhere where we don't know, but it still can simplify the math. Now, why each of these has drawbacks. So to be honest, I kind of feel like just putting it right here, just so that I don't have any negative numbers to screw up today. It's just, I'm feeling very positive today. Maybe it's the giant pile of caffeine in this massive cup. It's got to be it. Oh, I guess we're supporting Pioneer Valley today. That's cool. Whatever. All right. Yeah. Now, wait a minute. So Esteban, what was your question a minute ago before I started doing any work at all? I forgot it.
I said if the canoe is moving, because the canoe moves away from the dock, shouldn't the center of mass also move?
Yeah, and see, this is what's crazy. The idea is there's 2 different masses here. The zombie may move if the zombie, let's assume the zombie is heavier than a canoe, because usually people are heavier than the canoe they are in. Other boats, maybe not true, but a canoe, yes. So in this case, the zombie is going to walk this way. The canoe is going to slide that way under the feet. And as a result, the canoe will actually move more rapidly than the zombie due to its lighter mass. However, at each step they take, because we're ignoring any effects from the water causing drag, it's very easy to move this canoe back and forth when it's sitting in the water. The canoe will move to the left, that way, as the zombie moves this way, in just such a way that the center of mass never moves. If the assumption that external forces, net, is negligible is true. Did that address your question, Esteban, or not?
Yeah, I'm just trying to visualize it. It's kind of crazy. So I'm not picturing a center of mass, and as the canoe moves one way and the zombie moves the other way, but the center mass stays in the same place.
Exactly.
That's crazy.
Well, and so I could actually, I think, show you a simulation that we could do where we just move 2 objects and calculate the center of mass positions at every point in time. And what you could see is the center of mass, generally speaking, if you have objects moving at constant speed, they are moving towards the center of mass at different rates, but the center of mass doesn't change position. So that is also true. If you just do the math on it, that is true. Now, obviously, in the real world, it might not be this way. In the real world, sometimes frictional forces matter. If friction was present as the boat tries to move, then that assumption we made of external forces net being negligible would be totally false. And then the zombie might move more this way than the canoe moves that way because the zombie doesn't experience the same amount of resistive force. And then the center of mass could move. But if so a way I used to do this in class, and I don't really have the option here, is I would get a giant sheet of foam board and I would put it on top of aluminum cans. So I'd get 90. We used that. There was some like iced tea can that was really long. And we got like 50 of these iced tea cans and put a piece of foam on it and put a remote control car on it. And when you drive to the right, the road moves to the left because it's sitting on all these rollers. And you could measure the center of mass and see that this is not bullshit. It works. So just if you have 50 iced tea cans, a giant strip of foam, and a remote control car, and a lot of free time, rulers, go for it. But this actually does work. Cool.
So the distance the canoe moves, would it be the same as the distance that the zombie moves?
No.
It would be more, right?
Yes. So that's what's weird about it. They move, but they move different amounts. They have the same amount of force by Newton's third law. However, one of them's lighter. The one that's lighter will experience more acceleration. And then obviously you experience positive acceleration when you're starting from rest and start walking. And then when you're walking and come to rest, you have a negative acceleration, which slows you back down and stops the canoe again. So you're both at rest. You start walking. Whoops. Let's see if I can do this. Pretend this is the zombie in the canoe here. Whoops. Oh, okay. We're this way. Oh man. How about I do this? It's going to be hard for me. This is the zombie. This is the canoe. As I start walking this way, I push the boat back. And then as a result, I'm standing right here. The canoe is now moved to the left. I've walked the entire length of the canoe, but relative to the water, I've only moved this far, right?
So wouldn't you say you're further away from the dock than when you started?
Well, you get closer to the dock, but you just don't make it all the way, right? So again, right now, if I'm trying to do this to scale, my hand almost fits, right? Sorry, this is a weird demo. Okay, so as I walk, right now, my fingers are where the zombie is. Right? You got closer to the dock, but the canoe has moved so far away, you can't make it all the way to the dock. Is that helping?
Yeah, I'm not sure if I'm.
All right,
I'm
I'll show you. Yeah.
I'm thinking of the distance between the dock and the canoe. I'm sorry if I'm wasting a lot of class time right now because I know chapter 10 is really crazy. But so the distance between the canoe and the deck, if I was to call the canoe distance D, right, and then the distance between the deck and the canoe is going to be greater than D.
Let's get in here and do the math.
Okay,
because I think that's what you need at this point, and I think that's what everybody needs. And yeah, we're doing fine on time. We're doing fine. So, all right. So what I want to do is I want to call the dock 0. Okay. So this is my coordinate system. There's other good choices. Who cares? Let's pick one and go with it. So now the length of the canoe is L, right? I think that's what I called it. So, and let's assume the zombie is small enough it's a point mass. Not always true, but approximately true. So here's what I'm going to say. I know that the X center of mass initial is equal to I've got M1 plus M2 in the bottom. That's good. And then on the top, the position of oops, that's supposed to be purple. So I've got L over 2 times M2 plus L times M1. So first, let's see if that makes sense to you. The idea here is the zombie's all the way over here at L, so its X position is L times M1. The canoe's center mass is probably right in the middle. And so that's going to be L over 2 is its center mass. So again, the zombie, the canoe has a center mass right here. The zombie has a center mass right there. And so the center of mass between these two is probably, let me get another marker, closer to the zombie because I'm assuming the zombie is bigger. So let's assume this is the existing location of the center of mass. What I'm saying here is after you walk to the other end, I know the zombie is going to be right about here. I know the canoe is going to be here. Sorry, it's not perfectly to scale. The canoe's center mass is right here. And so notice it's supposed to be about the same, right? So the center of mass should still be here. And the idea is by walking to the other side of the boat, the distance between the zombie and the center of mass shouldn't change that much. I think the zombie was a big box, right? So that kind of makes it look a little better. So the center of mass is still the same distance from the zombie towards the middle of the canoe. However, our coordinate system over here shows us that we didn't get all the way to the dock. If I run the X center mass final, I'm still going to get two terms. I'm still going to have M1 plus M2. I'm still going to have something times M2 here. I'm still going to have something times, M1 here. And so now, what are these distances? Well, we could say that this distance right here, let's just call it D. So the location of M1 is D. The location of M2 is what? Where's the center of mass of M2 for this term?
Wouldn't that be L?
Nope.
No.
What's this distance?
Half of L.
So what's this distance?
Half of L plus D.
Yes. So far, so good?
Yeah.
Now, I'm running out of room here, so I'm going to scoot this back a little bit. I'm going to lower this down a little bit and just use the equations down here. The idea is I'm going to set this equation equal to that equation. That's the special thing we could do. Again, only if net external force is negligible can we do this. Whew. So then we could say, oh my gosh, this equals that. So D, I'm going to use just red for this side. Oops. Change my mind. I'm not going to worry about the basements because do you see they're going to cancel out in just a second? It's the same basement. This is sliding down a little bit. Let me move it up. So now on the other one, I got L over 2 M2 plus L M1. And then at this point, I'll bring it closer so that in case that's too small. Sorry about that. The idea here is now I could say, look, the denominators cancel out. Here I have an equation that has known parameters in it, except for the letter D, this unknown distance to the dock. And so what I could do is I could group these terms. We've got D times M1 plus M2, I think. And then here, I've got there's another term lingering right here, plus L over 2 times M2, I think, is equal to all this junk. I see that the L over 2 M2 drops out. And so now notice that D is equal to L times this junk here. And hopefully that's what we saw in the answer. Right there. Oh, so I used X, but yeah. So, all right, back to this. That's kind of showing you what's supposed to, how these problems work out. And I think we kind of beat this one to death now. I just wanted to show you that you can use center of mass in a weird way, and that was it. Do you feel a little bit better about that, Esteban, or no?
Yes. Yeah. So
cool, right? Isn't that
yeah,
wild?
it is cool.
Yeah.
So the distance between the canoe and the deck have to do with the fraction of their weights.
Exactly. So imagine if you did this in a power boat or some big heavy boat where your mass is a tiny fraction. Let's get that equation on screen. Let me get it up here just so we've got it. So here's the idea. M1 is zombie. So M1 is zombie, M2 is canoe. So notice if the zombie mass is small compared to your boat, the distance between there and the dock is negligible. So for example, if this was you standing on an aircraft carrier, if you walk from one end of the aircraft carrier to the other, you're going to make it to the dock. But if you do this in a canoe that weighs a tenth of your mass, or that has a tenth of your mass, then you're going to be, you're basically be only 10% of the way towards the dock approximately. Maybe it's 9%. I haven't thought it through, but something like that. All right. Now, if you are a physics person, this is probably important for you to see. So I'll mention a few other things here. I don't want to spend all day. Here's another one on here. If you wanted to understand the motion as they're moving relative to the surface. So this is kind of why Esteban was getting lost in it. It's a challenge problem. It's not that hard if you want to read the work. And there's one problem later in chapter 11 that comes back to this. So basically, if you want to understand the motion while they're moving, we need to use this center of mass velocity equation or the acceleration equations. Now, to be clear, I just want to show you here. Oh, let's do it on the whiteboard. I don't want to spend too much time on this, but take a look at this equation. X center of mass equals x1 m1 plus x2 m2 all over total mass. If the masses aren't changing and you take a derivative, you get the center of mass. Well, what's the derivative of x? That's velocity 1 times mass 1. If you take the derivative of this, velocity 2 times mass 2 all over m1 plus m2. Now this assumes the mass isn't changing. Can anyone think of a real life object that moves around through space and changes mass, moves around anywhere?
A rocket.
A rocket, a car, you, right? You sweat. So there's all kinds of objects in the real world that have changing mass, some of them to greater degrees than others. Rockets are almost all fuel weight, and then they lose a lot of their mass. So rockets are a good example. So if you're wondering, this equation doesn't really apply to a rocket. Perhaps you're wondering how to handle rocket science. Well, momentum does work. Do I do that on the next page here? Here's some more weird examples. That's cool. This is a good final review question. We'll leave that there for you to do in homework. If you're wondering how rockets work, 9.49 is a very interesting problem. So I'm going to let you kind of go through this on your own, but the fact remains, let's just start with these pictures and I'll kind of gloss over a little bit. Let's say you have a rocket that's moving here, and instead of thinking of the fuel as being liquid that gets sprayed out continuously, think of it as like a bunch of chunks, almost like suitcases of lead that you could throw out the back. By conservation of momentum, if you throw a suitcase out the back with some speed, the rocket should increase its speed a tiny amount. It's a simple momentum problem. The issue is you have to do it with differential sized masses. So for each tiny bit of mass, dm, that you throw out the back, the rocket loses a tiny bit of mass. So we get an equation. Let's see if we have this equation and just kind of guide you through it. As you can tell, these two problems are not generally my focus on final exam day. Again, the problems that we're looking at right now are not a huge focus on the final exam, but if you're a physicist, they're kind of useful. All right. So let's see. I think it's, whoops. Oh, there's the, here you go. So the conservation of momentum equation looks like this. You have mass times velocity for the initial rocket. Then you lose a little bit of mass, right? Right? The rocket loses a little bit of mass, but it gains a little bit of speed. Similarly, there's a negative sign on the part that gets shot out the back. Now, keep in mind, it's shot out at speed VE, but the rocket's moving forwards at speed V, so it's actually moving backwards at a speed less than the full ejection speed. So from there, you just use this procedure, do some math, and lo and behold, we get down to this equation, where mass times the tiny bit of change in velocity, and again, you should work through this and follow it through. I've done all the steps for you, ends up being the ejection speed times this change in mass with a minus sign. If you use separation of variables, that technique from chapter 2, we find out you get this weird logarithm appearing. So the final speed of the rocket is actually related to its initial speed, the rate at which you eject material, and the logarithm ratio of the masses. So if you start with a very heavy rocket filled with fuel and with a very light rocket empty of fuel, this will be a decent sized number. However, we see that the faster you can eject that fuel, the faster your rocket will go. And so that's the interesting part for everyone. And the math, you should be a physicist and do this if you're going to be a physics major. I think this is pretty interesting, actually. We see that if you can somehow squirt the fuel out faster by making it explode, right? That's why we're exploding these things and launching them out the back very, very, very fast. We get more speed out of our rocket. All right. Any questions about that? Well, I've got it up here. Again, it's just momentum, and then do some simplification of algebra, and then do some separation of variables. All right. And I think that's okay. Okay, there's some fun problems. All right. This is a good problem, 9.52. It's easy. It's a concept question. Let's do that together as a group. When an object hits the earth, it appears momentum is not conserved, right? So let's say you had a rock here and it's initially moving downwards with some speed v. Afterwards, it's going to hit the earth and eventually come to rest. It looks like momentum is not conserved. Like, let's say this was an asteroid coming in, a very small asteroid that comes, hits the earth, and then it stops. What's the story here? Is momentum conserved or not? Explain this conundrum.
Isn't the momentum transferred to the earth? The earth shifts down a little bit.
Exactly. It is still conserved. The earth moves down, but because the earth has such a huge mass, this velocity is so small, we can't see it. So it is conserved. We just can't see it being conserved. This has no momentum, but the entire earth is moving down, but because the mass is so large, we don't see it. Yes, that's it. Perfect. All right. So remember that in the real world, you're going to see this a lot where it looks like momentum is not conserved. And it's usually the case that it's hitting some extremely huge object and you can't observe that object's motion afterwards, even though conservation of momentum holds. All right. Let me see here. Okay, last piece. Remember when we did relative velocities earlier in the semester? If you are a physicist and you want to do beam physics, so talking about particle colliders and things like that, it turns out people use the center of mass frame all the time. Remember what I was just talking about, how we could have picked the dock, we could have picked the zombie, we could have picked the canoe, or we could have picked the center of mass as our reference frame. So in general, if you have objects that are moving, the center of mass, right here indicated by an X, will also move. What you could do is you could say, I'm going to let U be the velocity of the center of mass of my entire system. You could subtract that off of each term, and then the center of mass in your problem remains at rest. And you could take complicated problems and turn them into zombie canoe problems and do all kinds of beam physics this way. Then after you do that, you could add back in the center of mass velocity and find out their velocities in the real world. So basically, it's a trick you can do to simplify the math. This weird trick that I'm showing you is important to physicists. So if you're a physicist and want to understand all this, you can read all that. As long as external forces are negligible, we can use this trick. I think we made it. Yay. Okay, so that is chapter 9. I do want to go back to this one here, right here. I like this problem for reviewing for the final exam. I want to mention this while we've got it up here. If you look at this one, why is this a good problem? We have a graph you have to read. That's always good. And so from that, we know that if it's a YT graph, speeds relate to the slope. Now notice if the ball bounces, it hits the ground. There's a collision. From that, you could get the momentum before and the momentum after, and you could find out the force. You could also do plots and get the acceleration and things like that. So I think this shows you, and of course you remember in lab, we did videos, right? You could imagine getting a curve like this by making a video. And so this shows you a method for computing real life collisions and matching them up to this chapter. And as a side note, I actually know a man named Moon who kept getting emails intended for a man named Moon with 3 O's. And evidently they became friends. And this guy, I went backpacking with him. He turns out he's a pretty good engineer. Now he just got hired at Apple. I keep trying to get him to come here and be a guest speaker, but he doesn't want to do it. I don't know. He's kind of a shy guy. But I'll see if I could sucker him in, and I'll tell him we talked about him in class, and I'll tell him the whole class really wanted to hear him come talk. So I like guest speakers. I don't know. So we'll see if I can get Chris Moon to come in, and then you can say, is it true you got emails from the guy with 3 O's? And he can tell you. Any questions about chapter 9 before we move on? Let me get the grid up. It's really cool stuff. Oh, let me see in the chat. Sorry if that was waiting there a long time. Ha! Angel, I don't think that's going to work. He's probably making a lot more money than most of us will ever make. Yeah. He does all right. I don't know his salary, but yeah, oh, okay. I tell you what, I'll offer him some Taco Bell or maybe a Subway vegetarian sandwich. Yeah, he likes that. All right. I'll talk to him and see what he says. But other than that, any questions on chapter 9? You know what? This would make sense. I know it's a little early. Why don't we take our break early this time? It's the end of the chapter. And then I'll just stop the live stream and start it again. Don't let me forget. That way the live streams are better organized later. So let's go ahead and take our break now. So just come back at 12:55.